Welcome to day 4 of the Space and Geospatial Virtual Pavilion for COP26. My name is Andy Bennett and I'm the Space Lead at KTN. We at KTN are here to help connect for positive change. And by that I mean enable people from different communities, different parts of the UK and internationally, and different sectors to meet and collaborate. We want these new connections to enable change that helps, and in the context of climate change, we want these new connections to develop to help organisations meet net zero emissions or adapt and mitigate against climate change impacts. So far this week, we've had some excellent sessions, and particular highlights for me have included the Elements of Security session, looking at how climate change impacts on migration, and the session yesterday from Geovation, showcasing some up-and-coming startups who are helping to make our planet and supporting sustainable living their priority. I strongly recommend you go back and watch these sessions if you haven't managed to already. They'll be available to view for the next 90 days on the platform. I also encourage you to use the Virtual Pavilion platform to network with your fellow attendees. There are now over 1,300 registered attendees, and you can request a one-to-one with anyone on the platform, including the speakers from today. We also have networking tables open over lunchtime where you can join in with other participants and have unmoderated discussions. So now back to today. I'm delighted to introduce today's session on modelling energy systems and resilience, curated by KTN's very own Matt Butchers in collaboration with the University of Bath Institute for Mathematical Innovation. Before I introduce the chair, I'd like to remind you that we have a chat function where you can introduce yourself. And if you have any questions for the speakers, please use the Q&A function. These will be relayed to our panel at the appropriate time. So we're delighted today to have a very special chair for this session, Professor Vicky Pope. Professor Pope has a long and varied career in the Met Office, where she's worked for many years on climate change, leading climate model development, the wider climate programme, and acting as a public face for the programme. Before leaving the Met Office, Professor Pope was the Head of Science and Technology Futures and a member of the Met Office Government Services Senior Management Board. Professor Pope now holds many positions, including independent chair of mathematics in education and industry, a trustee of the Building Research Establishment, member of the EPSRC Mathematical Science Advisory Team. She is also an honorary professor at the University College London and founding editor-in-chief of Climate Resilience and Sustainability for the Royal Meteorological Society. I mean, I don't know how you managed to keep all those jobs going, but well done, Vicky. So thank you today for being with us, and I'll pass you over to the chair for the session to provide some opening remarks.
Thank you, and I hope that you can see my slides properly, so do let me know if you can't. Energy systems are obviously play a critical role in mitigating climate change, but I think what perhaps some people are not so aware of is that they also have susceptibility to the impacts of climate change. And this session today is really about the resilience and performance of energy systems and how we can use climate change information to help to make sure that systems remain resilient. I would say that the energy sector has been at the forefront of this consideration, I think, compared to other sectors, and I think there's other sectors have a lot to learn. So I'm hoping that in the audience there will be people from other sectors as well who will learn from this as to ways that they need to mitigate. Many aspects of critical infrastructure are weather dependent and actually may become more so in the future as climate changes and extremes become more frequent and more extreme.
Vicky, sorry, can I just ask you to go into, you're in presenter mode at the moment. Can you just go into full screen mode?
Oh, sorry, I should be, I don't know what's happened there. Let me just try again. I'm having problems with this. Sorry about this. Let me just share. Is that correct now? Still not right.
Very, very big.
I know. Yeah, sorry, I'm having an awful lot of problems with this. Let's try again. Is that one right now?
Give it a second. Yes, Perfect. Thank you very much.
Sorry about that.
That's
Sorry,
great.
we did practice this beforehand, but something went wrong. Right, so where did I get to? Yes, so it's important that in addressing these sorts of issues, one of the problems is that it requires a multidisciplinary approach. I think a lot of evidence development has become very specialized, and it's sometimes quite difficult for different sectors to work together. And that is something that's really important. So in this case, you want to bring people who are experts in energy systems together with climate scientists, for example, to solve the problem. And it's something that's very close to my heart. Fairly recently, I became founding editor of a new climate journal that's really looking at these sorts of issues as to how we bring different disciplines together. And I'll talk about this in a minute. And the other aspect I wanted to mention is that communication and dialogue is important in this. We all have jargon in our specialisms, and sometimes we use the same words to mean different things. So that communication is a really important aspect of this. And sometimes we need just simple tools to help decision makers to make these sorts of decisions. But of course, we need to understand the limitations of those simple tools as well. It's really important also, I think, that we understand the problem that we're trying to solve, so that specialists, for example, don't say, well, if somebody just understood my specialism better, they'd know how to solve the problem. Well, actually, no, you need to understand the problem. It's a two-way dialogue. And just a little illustration of this was some early work that was done by the Met Office in collaboration with the energy sector, led by National Grid. It was quite a few years ago now, 2009. But I often show this diagram because it's a very simple representation of a lot of work. It's a kind of burning embers diagram that you've probably seen in IPCC before, and it's got time along the bottom. And you can see that as things get more red, that means that there's more impact on that particular system. So you've got things like wind resources, coastal infrastructure, cables, transformers, and you can see that, you know, over time, as weather gets more extreme, it's having more impact. And it just allows you then, as a summary, to then decide how you drill down into those different aspects of the problem. Just to bring it more to the present day, this is something that Laura, one of our panelists, gave me, which is just looking at how we can provide information to the energy sector. And it's really targeted, very detailed information from the climate change projections to provide useful information that can be fed into decision making. So it's looking at future renewable configurations in the UK energy system, for example, how they can be rigorously stress tested based on weather and climate resilience. And it's putting together plausible scenarios, plausible alternative realities that people can test their systems against. So I won't go into detail here, but obviously it's brought together different experts from National Grid, Ofgem, the Energy Systems Catapult, and so on. And these are tools that can then be used for looking at these sorts of problems. So just to say a little bit about the journal that I mentioned. So it's called Climate Resilience and Sustainability. You can see the cover of the journal behind me. I should mention before anybody asks that the building in the middle is there are actually two of them. It's in Milan, and it's the I've forgotten what the name of it is now. Anyway, but basically it's a green. The idea is a green building. It's got plants all around it. They did have to put more concrete in the building to hold up all the soil and the plants. And they have to do abseiling to do the gardening here, which is interesting. But it does mean that the inside of the building, for example, is much cooler than the outside in the summer because it's got natural air conditioning, if you like. So it's just some interesting concepts, I think, that have been turned into reality, which is an illustration of the way that you can try innovate new things which allow you both to adapt and mitigate climate change by reducing energy usage, but also making a more comfortable environment. So the journal is really about attaining the Sustainable Development Goals in the context of climate change, and really how one environmental or societal challenge can affect another. If we think we can reduce emissions by introducing diesel cars, for example, as was done in the UK a few years ago, did we really think properly about the implications for air pollution? So it's really about looking at a problem in the round, about actions that work, actions that don't work. We're really interested in publishing things that don't work as well as that do work, because it's important to understand those. And it's very difficult often to get people to do that. To look at co-benefits and trade-offs, I just mentioned, and also to look at complex systems. The journal is open access. I think this is a very important part of it, really, that the information is available to everybody. And as well as research articles and review articles, we're also encouraging policy and practice papers. So we get practitioners as well as researchers to publish here, short communications for early research. And it's very early days. We've only got a few papers so far, but I would like to encourage impact summaries as well so that it's more widely accessible. Just to give an idea of the kinds of things that we're including, it's really about that interplay between the different aspects. So you've got the kind of core climate change, temperature rise, storm surge, etc. And then how that interacts with development, energy and technology use, production and consumption patterns, things like deforestation, land use change. And then obviously as that relates into human systems, food systems and water resources, etc. So it's really about that interplay. And you can see from that we need very different disciplines to publish here. One of the challenges, of course, and maybe some of you might be able to help with this, you can volunteer later, is finding reviewers for these papers is difficult, because actually having people with the expertise, they're not going to have the expertise across the systems. And you also sometimes find with multidisciplinary papers is that they're not up to the standard in one particular discipline that you would get in a single paper. And that can make reviewing quite difficult as well. Something that can seem obvious in one sector is not obvious in another sector. So all of these things I think are challenges, and I think they're things that affect the kinds of things that we're talking about today. So just moving on to the agenda for today. Chris is going to talk in a minute, and I'll introduce him in a sec for half an hour on mapping the impacts and visualization of extreme weather on system operation. And then we're going to have a panel discussion with Chris and Laura from the Met Office and Jonathan from National Grid. I'll introduce them later. And then we're going to have the challenge introductions, which Matt will introduce later on, and finally some closing remarks. So I will just introduce Chris and then he can share his screen. So Professor Chris Budd is known for his contributions in numerical analysis of nonlinear partial differential equations and their applications to industry. And I think particularly, I mean, I know Chris is a passionate popularizer of mathematics, and he was awarded the Order of the British Empire and the Queen's Birthday Honours List in 2015 for services to science and maths education. Most recently, Chris has taken up the position of Director of Knowledge Exchange at the University of Bath Institute for Mathematical Innovation. So I'll hand over to Chris now to introduce his talk. Thank you. Chris, you're muted.
Thank you very much, Vicky, and good luck with your journal. So I'm going to talk about a project which is a joint project between the University of Bath and the National Grid electricity system operators, Jonathan Barcroft being one of the collaborators who is here today. And the project was called MIVOR, and MIVOR is mapping the impact and visualization of extreme weather on system operation. And you can see there the various collaborators that put this together. So it's a team from the University of Bath and a team from ESO at the National Grid. So I think it's well known that the majority of the world's energy is now supplied by high voltage electricity. And as we move away from burning fossil fuels to a carbon-free economy, the use of electricity is going to increase and increase. So an obvious area is going to be the use of electrical vehicles and the charging thereof. So this is going to be a huge change of the electricity supply industry in response to climate change. And the National Grid ESO exists basically to make sure that this happens and that we get a reliable and secure system, and that the system that we have ensures that the electricity is always there when people need it, both in normal operation and in extreme cases like when you've got a big football match or something like that. And the ambition of ESO is to operate, is to move towards having a zero carbon system really in the near future. So if you get it wrong, things can go very badly wrong. In 2003, there were a combination of failures of the grid in the Northeast US, which led to a blackout. And in this picture of the US at the top right, what looks like the sea is actually the area of the Northeast, which went down when the electricity supply failed for some days. And I say this was a combination. It was triggered by a power cable failure, but then there was a system cascade, which led to this much bigger failure across this very large area. And that led to a cost they estimated of about £5 billion to the US economy. This has not happened in the UK, largely due to the good operation of the national grid. But keeping the lights on is very, very important to the general public and, of course, to the politicians attending COP at the moment. The security of our supply is paramount, and yet the energy system is going to be greatly affected by climate change as things change into the future and we get more extreme events and higher temperatures. And it's extremely important that we then future-proof the electricity supply industry against the effects of climate change. And the purpose of the project that we had with the National Grid was to look at the sort of impact that climate change is likely to have on the operation of the grid itself. So electricity itself is supplied over a complex network, and this is one reason that we have to be very careful about looking at the effects of climate change, because you have a number of different types of generator of electricity, from renewable through to fossil fuels and nuclear. We're going to hear a bit more about some of these later on in this session. And then that's transmitted to the user through both high voltage and a low voltage supply. And then we have consumer demand, which is going to change with things like EV charging and other things. So it's a very, very complex system with many components. And this is one reason it's actually rather hard to assess the impact of climate change on the whole system, because it affects different parts of the system in different ways. But we're mostly going to today have a look at the impact on the high voltage system. This is the extra high voltage grid operated by a combination of operators. So we have the English and Welsh electricity supply, and obviously we thinking in terms of COP, there's the Scottish energy system as well. So that's what we're trying to look at, and look at the impact of climate change on this. And one of the effects of kind of going towards a low carbon economy is that the relative proportion of the different types of generator has massively changed in the last 20 years. So at the beginning of the millennium, the greater majority of our electricity was generated by fossil fuels, with quite a lot of the remainder by nuclear and a tiny proportion by renewables. Now we've got to 2020, we've seen a 5-fold increase just in the last decade of the use of renewables, a drop in fossil fuels by nearly 60%, and a slight drop in the overall generation. So this is a huge change that we've seen really very, very recently in the move towards renewables. And obviously that's, again, going to have issues to do with climate change, because not only do we want to have more renewables to reduce our dependence on fossil fuels, but renewables are impacted by climate change in different ways from the use of fossil fuels. In the future, we're predicting a huge increase in the demand for electricity. Again, this is due to the move away from a carbon-based economy. The current generation is about 60 gigawatts, and it's going to move by 2050 to around about 100 gigawatts with various scenarios. And what the National Grid is looking at are various different types of projection, consumer transformation, system transformation leading the way, and steady progression, which are 4 different scenarios depending upon various high-level political decisions for the generation of electricity into the future. And we'll look later on at the way that these four different pathways to this high electricity demand are impacted by climate change. The generation mix is also going to change. As I said, at the moment, we have quite a lot of renewables. That is essentially going to increase a great deal. So by 2050, in these various scenarios, we're looking at the greater majority of our electricity being generated by a combination of renewables, that's solar, offshore wind, biomass, and so on. And you can see on the right the various mixes that we're going to have. So let's have a think now about climate change and how we expect this to impact on the electricity supply industry. There are basically three significant impacts of climate change, and we're going to have a look at all three in a bit of detail. One is failure rates. So as the climate changes, so we expect more extreme events, we expect more extreme storms, more flooding, and higher temperature days. And one of the impacts of the extreme events, for example, high wind, is to lead to more failures, particularly in overhead lines, OHLs. We'll have a look at this in a minute. Another impact is on changing supply. So climate change is clearly going to impact on renewables because they rely on things like the wind and so on. But also the general change in the temperature affects the efficiency of the operating plant that we have. And that changes our ability to supply electricity. Thirdly, demand is going to change. So we're going to have more electrical vehicles, they need to be charged. As we move to higher temperatures and hotter days, so our air conditioning systems are going to be used more, and that's again going to put a strain on the system. We're also going to see less cold, really cold days, and therefore our heating demands are going to change. So the project that I'm going to talk about, the MIVOL project, then used a mixture of analytical and statistical modeling to assess the impact of climate change on each of these things, the failure rate, the supply, and the demand. But one thing we didn't have to do in this project was actually do the climate predictions. And I don't know how many people are familiar with this, but the UK Hadley Centre has produced a set of predictions called the UKCP 18, which are freely available data sets of projections of the climate up to 2050. And these are done on a fairly high spatial resolution. They're on a 12.5 kilometre grid for the probabilistic forecast. And they give monthly average data for the climate up to 2050. And when you use these, they give you 8 weather endpoints you can use. We have 3 temperatures, that's minimum, maximum, and mean, wind speed, humidity, pressure, precipitation, and sunshine hours. So this is a mass of data which we can then use to look at projected climate into the future. And the way that UKCP works is they produce 12 equally valid climate forecasts, so you have an ensemble, and that allows you to then make probabilistic forecasts of the impact of climate change on various bits of operation. This is the UKCP 18 website, and there you can see the team that put it together. And as I said, this is a freely available resource. It's a very large data set, but you can kind of register for it and then use it. And here's an example of the various things that it can do: regional projections, marine, probabilistic projections, and derived projections. And headline result, we're going to get a greater chance of warmer, wetter winters and hotter, drier summers. So if you're not familiar with this database and you need to do climate projections into the future, I very, very warmly recommend that you get hold of it and use it. And one of the ways that the UKCP operates is that they have a number of what are called representative concentration pathways, RCPs, for different projections into the future, depending upon different political decisions, which are being made, of course, at the moment at COP. So if we do very little to change the way we work into the future, the predictions are of an average increase of 3.7 degrees centigrade by the end of the century, and significant sea level rise and significant increase in extreme weather. So that's RCP 8.5. And the best scenario, where you go to renewables and also capture all your carbon dioxide, is projecting a 1 degree centigrade rise and a small increase in extreme weather, and that's RCP 2.6. But the National Grid asked us to do our projections looking at RCP 8.5, which is the worst case scenario. And let's hope we don't go to that one, but that's the one we looked at. The UK, also, the Met Office, the Hadley Centre, also produces a large amount of historical data, which is extremely useful, from 1862 to the present, with high temporal resolution and lots of data as well on the different variables. And again, this is extremely helpful in assessing any sort of model and looking at the way of calibrating that model against historical weather. And again, this is freely available data which we can all use. So let me tell you now about the MIVOR project. So we had available to us this historical data from the climate and historical energy data. And we also have a degree of physical understanding about the way that climate impacts on various aspects of the electricity supply. There's quite a significant literature on this. We then developed two approaches. One was to use the physical understanding to develop analytical models, which gave us model-driven forecasts, informed then by the climate predictions on the UKCP 18. And on the other side, we had statistical models which were generated by looking at the historical climate data. So the team we had was a combination of mathematical modelers, electrical engineers, and extremely good statisticians. And then the statistical models allow you to do data-driven forecasts of network failures and other types of events. And the two kind of A and B, the analytical models and statistical models, then give us a very complete picture of what we expect to see going forward. And using the kind of ensemble predictions from UKCP 18, we can then get probabilistic estimates of the kind of range of things that we might expect to see. And the various forecasts from this were then things like the temperature demand, impact on demand, temperature impact on generation, the impact of wind on the network, and the resulting forecasts and network failures, and things like the extra demand that we might expect due to changes in the way we do our heating and so on. So that was the general MIVOR methodology. So let's have a look then at the results. So we're going to have a look at three things: failure modes, generation changes, and demand. So we'll start out with failure modes. Just to say a little bit about my background, before I joined the University of Bath, I worked for a while for the Sintram Electricity Generating Board. And whilst I was working for them, we had the hurricane that hit the UK in 1987. And one of the jobs of the group I was in was to look at the impact of that on the pylons. And this is a photograph of a pylon that we took during that, just after the storm, where you see pylon failure, in this case, due to hurricane force winds. So historically, if we look back at the historical faults, this is a chart showing the various things. The majority of the faults in the period we looked at were overhead line transient faults. So these are typically where a cable might, in high winds, come into contact with a tree or something and temporarily has to be shut down. There are also overhead line permanent faults. This is where our pylons are blown down or there is more severe damage to the kind of transmission network. Then you have transformer faults, which are where the transformers in the substations typically fail, often due to some sort of flooding. And else is the various other bits of equipment in the substations. There's lots of other things that are going on. And you can see kind of the distribution of the types of fault. Here we can see, this is a meeting, of course, on geospatial stuff. So here we can see the kind of way the faults are distributed. Again, the majority of the faults are the overhead line faults, and they can occur pretty well anywhere in the network, but the most vulnerable parts of the network are those where you're most likely to get high winds and also where you've got longer cables. So there's a very strong relationship between the length of a cable and the likelihood of a fault due to high winds. And here we can see again the various proportion of the number of faults that we expect to see, with overhead line transient being the dominant one. So given that the majority of the faults are transient and are due to wind, this is an absolutely clear area where climate change is going to affect the electricity supply, essentially due to wind blowing on the cables or very high winds causing failure of the pylons. So here is a statistical study again of the overhead line transients. This is sort of showing what you can do with historic data. And we found that a negative binomial distribution really fitted this pretty well, a distribution which is then informed by things like predictions of the wind in any one month. So that was the kind of statistical model that was developed in the course of the project. Just to comment on the historical faults, the faults that we're looking at are very unlikely mostly to cause a significant loss of demand. The national grid have been very successful in keeping the system working, and the system is designed to be secure. The reason the Northeast US went down so badly was that they had a failure in their essentially in their system operation, which we haven't seen in the national grids. So don't get too worried by the faults that I've just shown you. Okay, and here's again the bar chart of sort of flow chart of how we then developed the models, where we had the sort of semi-empirical physical models which allowed you to predict the likelihood of a failure of an overhead line in high winds, and also the likelihood of a pylon blowing down in high winds. Obviously, this is something you can go off and do experiments on. So we had these sort of models available to us. So let's look at the predictions. So here is the overall prediction. So in the kind of period of up to 2050, where we're kind of looking at the impact of climate change on the network, we're expecting to see a sort of 5% or thereabouts increase in the number of faults due to overhead line failure. So that's transient fault. So it's a 5%. So it is a significant increase, 5%, but it's not particularly worrying, but it's there. It's a 5% increase. There's a larger increase in the faults likely due to be the else equipment, but that's a much smaller number in the overall number of faults that we expect to see. So the majority of the faults will be due to overhead line. And on the right, you can see where the largest number of faults are going to be. So you can see there's a nice blue blob pretty well sitting on top of COP actually, where we expect the largest number of faults to occur in the west of Scotland, mainly due to the high wind there, and a number of faults, particularly in the southeast, where the system is there's much higher demand and there's much greater sensitivity of supply down there. Here's the general prediction of failures in the periods we're looking at. So if we go to the extreme right, we can see there's a shift from 1085 in the current and transient number up to between 1120 and 1144. That's our confidence interval for the overhead lines. Transformer faults are not going to change particularly. Overhead line faults are actually going to drop a bit, permanent faults, and then quite a big increase in the equipment faults, although that's a much smaller number than the overhead line. So there will be an increase in the amount of failure of the electricity supply, the overhead lines and so on, but it's not going to be too brutal, but there will be an increase. Just a comment on the else equipment. So although the increase is percentage very large, that's on a fairly small number of things, and there's an awful lot of things going on there, and substations are generally fairly well protected from the weather, and so we don't expect climate change to really cause too much damage on that. Just to show you how the overhead line failure is going to work. So here are two predictions. On the left is 2025, on the right is 2030, and you can see where the majority of the failures will be, particularly in the spring and in the winter, where the large number of failures are going to be. But as going into 2030, we're going to see a significant increase in the number of failures in the autumn due to the changing wind patterns predicted with climate change. And this is the probability of overhead line failure. So there are various larger years coming out of the climate predictions, 2026 and 2042, both are leading to higher changes than in other years. Again, that's following from projections. So let's move now on to generation. So the change in temperature that we're expecting with global warming is going to cause a number of risks to generation, which then affect the whole supply chain. One of the impacts of climate change is that we expect to see a large increase in the number of extreme temperature days. So this is historical data, and hot days really do affect generation. They affect generation in a number of ways. They reduce the efficiency of conventional generation. They reduce the efficiency of nuclear generation. And if you've got wind generation, then the change in the air density actually changes the amount of energy you can get out of a wind turbine. So hot days lead to stress on generation. So in the near future, we're going to have high risk in the southeast, which is going to be the first place which warms up. And as we move to 2050, areas which are currently are of low risk are going to get more risky as the temperatures increase, especially if we go up to a temperature increase of about 3.7 degrees. So generation is going to be impacted. Here are the predictions from MIVOR. So on the left, you can see the change in temperature as predicted by UKCP across the UK, with the southeast and southwest really getting quite significantly hotter. And on the right, you can see the change in generation variation by this temperature change. So that is actually quite a significant change. Just to finish, I want to talk about changing in demand. So there's going to be a significant change in demand, mainly due to electrification of heating, also due to the use of electrical vehicles. And one of the things that will impact us significantly is the increase in the amount of air conditioning on particularly hot days. This is much harder to assess using the models that we have, because all of these things, instead of being dependent upon physics, are largely dependent upon people. So there's a bit of a kind of rougher modelling about the way that demand will change, but certainly as we move to hotter days, we do expect to see significant changes in demand due to air conditioning and the change in the way we do our heating. But at the same time, because we're going to be warmer in the winter, we may need less heating. So there's a bit of a balance there. And there's a graph showing the way that various things change the demand. So the dominant change in demand is going to be due to temperature and also due to changes in precipitation, where the other effects of climate change like wind speed, sunshine and relative humidity have less impact. And just to show a final picture, and I've got one more slide after this, Vicky. This shows a picture of the cases where you get a combination of generation demand stresses due to climate change. And these are predictions of sales in the UK, where we expect to see extreme changes. So the main areas are the central belt across Scotland and the areas around the southeast, and particularly around London. And just to conclude, energy manages to us all, and supplying enough energy is a very important challenge. Our networks are very sophisticated and are going to get more and more complex as we move to different ways of generating electricity. Climate change impacts on all aspects of both energy supply and demand and on the faults of this. But by using a combination of historical data and climate predictions, we are able to make reasonable estimates of what this challenge will be. So thank you very much, and I will hand over.
Thank you, Chris. So we're going to have a panel discussion now, and do submit your questions. We might have time I've got a few already, but we might have time for a couple more. So Chris will be on the panel, and also Dr. Laura Dawkins from the Met Office. She's a senior statistical scientific consultant in the industry consultancy team. And Jonathan Barcroft, who's a senior data scientist at National Grid ESO Lab. So welcome to all of you. If when you answer a question, if you could just introduce yourself, say a little bit more about yourselves, that'd be great. So the first question is one that I'm going to initially ask Jonathan, but I will ask the others to contribute as well. What are the greatest challenges for the energy sector in adapting to a changing climate over the coming decades?
Good morning. I'm Jonathan Barcroft, a senior data scientist at National Grid in the Electricity System Operator Labs team, responsible for short-term forecasting of demand and renewable generation. I've been the business lead, as Chris mentioned, on this MIVOL project. At National Grid ESO, we're responsible for reliable and secure system operation to deliver electricity where customers need it. Our ambition is to be able to operate a zero carbon system by 2025 and achieve net zero by 2050.
Oh my God.
Looking at the risks of extreme weather to the planet power system. Looking at the risks of extreme weather of the power system over the next 30 years sits with our long-term forecasting activities. The MIVOL project has given us the opportunity to use these UKCP 18 climate projections to be able to predict what the effect will be on these challenges under a changing climate. So we consider these challenges under three primary levers. We've got the networks risk, we've got a generation risk, and we've got a demand risk. And we need to model each of those and understand what effect that's going to have over the next 30 years. Every component of the power system is affected by the weather. It's exposed in the natural environment. So it's important that we take that into effect in our long-term methodologies.
So just coming back to the question, what would you say the greatest challenges are based on the work that you've done?
So primarily those network risks. So we've got the increasing risk of exposure to storm damage or increasing temperatures causing reduced ratings on the transmission network or distribution networks. On the generation side, we've got the thermal efficiency of plant. So warming, cooling water make the thermal power stations less efficient. And also the potential of extended periods of drought, for example, could restrict hydro generation. On the demand side, we've got a changing energy system where we're moving towards the electrification of heat. And that's going to drive, potentially, if we have increasing high temperature summers, going to lead more people to installing air conditioning, which will change the demand profile over the course of the year.
Thanks. Laura, now you've stopped being attacked by your plant. Did you have anything to add to that?
I'm sorry about that. That was my cat trying to get my attention. Yeah, sorry. So thank you for having me along today. I'm Laura Dawkins. I'm a senior statistical scientist at the Met Office. My background's kind of in statistical modelling of extreme weather and climate. And over the last about 3 years, I've been working on energy related projects at the Met Office. So yeah, I think in my experience, to add to that, one of the key challenges is actually in how to quantify the challenge, how to actually capture the effect of climate change, but as well as that, climate variability. So I think Chris was saying about how we need to use historical data as well, but we also need to use a really long record of historical data to properly capture how the climate varies, which actually causes some of those really extreme events to occur. So I think there's a challenge in kind of getting hold of all of that data that you need. And then also, I think, as you alluded to, Vicky, is in the computational challenge of actually using all of that data, and how do you kind of use that within complicated energy models to capture the challenge.
Chris, did you want to add anything?
So I would obviously agree with everything that Jonathan and Laura said. I would add to that, I see it's not really the impact of climate change, but more the impact of the way we respond to climate change, which we're going to have this huge shift over to electrical vehicle charging. And to put it into context, the average kind of customer household is taking about 1 kilowatt on average out of the network. When you're starting to charge an electrical vehicle, that's going to require 1 kilowatt or more on its own. So we're going to see a significant increase in the need to provide electricity to charge these vehicles. And that obviously is going to change the way we have to supply electricity. And by the way, I think this is a very good thing, but it's something that has to be planned for and thought through.
Thanks, Chris. So I'm just going to move on to the next question now. This is one I'm going to direct at Laura first. What are the biggest opportunities for new products, processes and services which arise from these challenges, and with a particular focus on the role of geospatial data, as this is obviously the Geospatial Pavilion? So,
yeah, I think these challenges bring up loads and loads of opportunities. I think it's the key kind of challenge, I think, is in around, and I think the energy sector is sort of pioneering, is this needing to take decisions and take actions that will both mitigate climate change, so decarbonising the energy system, and also adapting in a resilient way, so trying to understand that kind of balance between mitigation and adaptation. And I think to do that, the energy sector needs information and understanding of what weather will impact future kind of renewable configurations of the energy system, as well as kind of current day systems. So I think this brings up the opportunity to produce kind of data sets and information such as the stuff that Chris just showed us around what those kind of weather impacts will be, and sort of boiling down all of that information and data that we have at the Met Office and other kind of climate centres to actually really provide key kind of stress test data sets that could be used to understand that kind of trade-off between mitigation and adaptation. And that's kind of the sort of data set that we were trying to develop in the adverse weather project that you introduced in your slides, Vicky. So that's a project we worked on with the National Infrastructure Commission and the Climate Change Committee to develop these sort of, they're more focused around demand and how that may be a challenge in the future. So looking at kind of wind drought scenarios. So yeah, the opportunity to develop these kind of data sets, and they obviously must be geospatial in nature so that we know what's happening where, and so the energy sector can understand the kind of trade-offs and balances that they need to manage when those kind of extreme weather events are occurring. So I think that's one of the kind of opportunities. Another one in more of a kind of short term is actually providing products and services that will allow the energy sector to better use and understand how weather forecasts, so short and medium term weather forecasts, can be used to better manage that kind of day-to-day variability in weather. Because if you're better at managing that currently, you'll be able to kind of intrinsically be more resilient to the types of weather variability and weather extremes that may occur in the future. So an example of this is a project that the Met Office are doing with National Grid, looking at how we can kind of use knowledge of weather forecasts to optimize the transition network. So it's the project called the Dynamic Line Rating Project. And so understanding how you can use the network to its maximum potential without having to kind of build more infrastructure. And then finally, I think another opportunity is around developing training. So trying to understand and bridge that gap between the energy sector and climate sector. So something we find at the Met Office is often organisations find it challenging to take all of that UKCP18 data and use it for decision making. So I think providing training in how to kind of do that is really valuable sort of thing that we can provide, and actually it's something that the Met Office have started recently running. We had some energy sector participation in that in September, which I think they found really useful in understanding how to use the data for the actual decisions that they need to make.
Thanks. I think I should ask Jonathan to comment on that, actually, as a kind of recipient of some of this. So.
I think everything that Laura said there answers where the priorities are. The difficulty comes with applying these data sets into industry. So being able to take these projections and being able to align those to our power system models is quite a big step in making sure that we've got an aligned, transparent, and sort of cohesive method to delivering that is an important activity for us.
Chris, did you have anything further to add on that?
I'd like to say that the data that UKCP18 has is very clear, and whilst training is useful, it's not impossible for sort of someone used to data science and used to handling data to access and understand the data set. It's very clearly presented. So yes, training is vital, but don't let that put you off from using these excellent data sets.
Okay, I'm going to come to a more general question about gaps in a minute, but I wanted to raise a question that one of the people in the audience has raised, which was about wind data. So I know, as I was involved in the UKCP09, that the wind projections were not very reliable in terms of what we expect in the future. And I just wondered if, and that's obviously come up as a critical element in the infrastructure that we've been talking about today. And I just wondered whether the UKCP18 winds are up to really giving good projections of what might happen in the future in this context, whether, Laura, you might be able to comment on that.
Yeah, so I think there are always challenges around modelling wind, and I'm not an expert in the kind of validation of the UKCP18 wind data, but from my experience, I think it's still a useful tool. And I think although the projections can show kind of different directions of change, that's still quite useful information in terms of capturing the uncertainty that we might have about how winds might change. And also the direct impact that might have on extremes is still kind of worth exploring, I think, using those projections. So I think there isn't, like temperature, there's a clear signal. There isn't a clear signal in wind, but I would say that that is still a very useful tool. And I think particularly UKCP18 has these very high resolution projections that have been produced, so the 2.2 kilometre local projections, which are trying to solve some of those problems that maybe occur from not having the kind of high resolution modelling underneath them. So maybe worth looking at those, I'd say.
Yeah, so I'm going to broaden the question. Sorry, Chris, do you want to comment?
Well, if I can just comment. So
yeah, of course, yeah.
We were primarily using lower resolutions, the 12 kilometre, and we were mostly using monthly average wind rather than extreme wind predictions. So that's a more reliable. Obviously, it's easier to predict the monthly average than it is to predict an extreme wind. So we were mostly relying on that, although there are, of course, links between monthly average and the likelihood of extreme events as well. So we use some of that as well.
So I'm going to delve into this now that you've mentioned that, but how did, because it's the extreme events that cause the failures, so how did you translate those monthlies into extreme events if you weren't using the data?
Well, because we had all the historical data to use for our modelling as well. So you can look at the historical data, which it converts into the link between the historical data and extreme events, and then project forward using for the UKCP forward. So that's how we were doing it. So
I'm going to end up with a discussion with you about that, but I'll do that another time.
Yes.
So I just wanted to ask you just generally what the gaps are in understanding, and obviously you can comment on the winds as part of that. What are the gaps in understanding and how can we address these? And what examples can we learn from other sectors? So I don't know, Jonathan, do you want to go first?
So I mentioned in the previous question, one of the biggest challenges we've got is identifying the relationship between the climate parameters and our power system variables. So being able to tie those into our business models and create aligned climate projections. So we're looking at developing more interoperable digital twin models of the power system to be able to model all of those at once. So you see the combined effect of changing temperature on changing demand and generation at the same time in the same model. So that's our current approach for how we're addressing them. Yeah.
So Laura, did you want to add anything?
Yeah, I think kind of linked to that, what is something that I think both I and Chris have experienced is a slight kind of mismatch in the resolution of data that's required in a temporal sense. So I think my understanding is energy models work on a sort of half-hour to an hour resolution, whereas climate data is often at a lower resolution, and it's generally intended to be used to explore kind of temporal trends in weather variables rather than necessarily the kind of hour-to-hour variability. So there's a kind of gap there maybe in understanding between the two sectors, and a gap in communication around what are the actual questions that the energy sector are trying to answer, and is the climate data able to do that and useful and the tool that is needed to do that, or is there more work needed to kind of bring those two together? And so I think that's a gap in understanding and communication.
Chris, did you want to add anything?
Well, as I said in my talk, whilst we can understand the impact of climate change on equipment and failures, much harder to understand the impact of climate change on demand, because that's very much a human thing, and that also involves things like agriculture and many other aspects where electricity, transport, whatever might be used, and modelling that is obviously extremely hard and not something we can easily do. So any work on climate change, the impact of climate change on any system, is incomplete without at least trying to make some sort of understanding of the way that human beings are going to fit into the picture.
And so sorry, Laura.
I was just going to kind of echo that, and that was something that we found in our project. So we were aiming to look at how demand might change in the future, but it was very much based on an assumption around how cooling demand may change. And I think, as you said, lots of work needs, but more in a kind of societal behavioural understanding kind of way into how that might change, and are there actually alternative technologies to using air conditioning, like kind of growing lots of plants up our buildings and that kind of thing that will avoid these challenges with the energy system.
I like the picture behind me, which
Yeah.
may use less energy when it's built, but it produces a lot of CO2 to build it because it had a lot of concrete in it. But so that, you know, this is where the trade-offs are important, I think. So, Chris.
Interesting. I mean, we're seeing very rapid change also. I mean, the uptake of electrical vehicles is very rapidly increasing, and clearly that's being led by factors, political factors, for example. And who knows quite where we're going with that, but I think it's very likely that most of us will be driving an electrical car in the next 10 years, I would have thought. So, but we have to try and predict that.
So I've got another question here, which is quite a specific technical question, but I think it relates perhaps to the one that we just asked, really, and how models account for all the other factors that affect performance. And so this particular question is, how do the Myville models account for the spatial data on predicted ash dieback on distribution network faults, probably increasing permanent fault frequency? What might implications for increased woodland management and monitoring and remediation be? So obviously that's very specific, but I think there's lots of things like that, you know, kind of things that we don't know about happening that also affect, and how are they built into our modelling approach? So Chris, this is one for you, I think.
Well, the very short answer is that the Myville models don't have that in, and that's an extremely interesting observation that the questioner has posed. I mean, so we didn't account for that. We looked at wind, we looked at rain, we looked at snow, we looked at high temperatures and low temperatures and icing and all of that. But yeah, there's all these other factors, and we didn't include those in, and it's clear probably that we should in the future as we develop and extend these models. So very, very good observation.
Jonathan, do you want to comment on that?
I think it is quite complex, all these different feedback loops that are going to interact with each other with that changing scenario. One thing that may help us in that regard is that a lot of networks tend to manage vegetation in close proximity to their assets. So there tends to be a strip either side of the asset where vegetation is cleared. So there's perhaps growth modelling needs to be taken into account to see how regularly that sort of work needs to be carried out. But I don't know that it'll increase faults necessarily as much as maintenance.
Laura, are you able to comment? Because I know the Met Office looks at how climate change will impact on vegetation as well as systems. Are you able to comment on that at all?
I wouldn't say it's necessarily my area, but I think that's definitely a very key part to include in this thing, in these kinds of analyses. Yeah, I know there's work in the kind of rail sector around exploring leaf fall on tracks and that kind of thing. So it's definitely something that could be extended, I think, to the energy sector in understanding how vegetation interacts with the infrastructure. Absolutely.
Yeah, thanks. And I've got a question here. It's kind of the final one I've got, actually, but I think I wanted to bring it in two parts, really. I noticed, Chris, in your talk, I don't think you talked very much about the probabilities. So the UK climate projections, there's a lot of uncertainty around the projections, obviously, and that's reflected in the probability distribution. Yeah. So I don't know whether you want to comment on that first, and then I'll ask the other question.
What we did was we used the ensemble. So the UK CP18 doesn't give you one forecast, it gives you 12, an ensemble of 12, which are equally valid. And so that gives us the spread. So that's what we use to give the probabilistic forecast. I mean, and that was compounded also by the fact that all of our statistical models are necessarily probabilistic as well. So that's how we built it all in.
And were there areas particularly where that uncertainty was more pronounced, would you say?
Well, rainfall's very uncertain. That's particularly pronounced, although that seems to have less impact on things than other. And then the one that we've alluded to earlier, and I'm sure Laura can comment on, is the probability of extreme events. So that the joke being that extreme events are hard to predict. You know, so trying to understand what the probability then is if you've got a mean temperature of a mean wind speed of a high wind in an area where you happen to have a power cable. You know, at the end of the day, that it has to be a probabilistic thing.
Yeah. So the final question really is that is around communication of probability. Well, all of this complex data actually, because you've got, you know, there's quite a lot of complexity in the projections. Then when you translate that into how you use that in your decision making, how do we communicate that to decision makers, particularly talking about probabilistic forecasts, where we want people to be able to use this information who aren't specialists, who haven't looked at these things in detail. So I don't know who would like to go first.
I can have
Laura?
a go.
Yes,
yeah.
you.
So I think this is obviously a challenge that always kind of comes up, and I think people obviously understand that we can't predict the future, and are kind of comfortable, I think, with the fact that the future is uncertain, but that obviously then needs to be used in some way to make decisions. So I think there are kind of frameworks out there, kind of statistical frameworks for making decisions based on kind of uncertain information and kind of probabilistic modeling. So those kind of techniques can be used where you essentially have your kind of maybe two or three or whatever decisions you need to make, and based on all the alternatives that could occur, what's the sort of optimal outcome based on those kind of uncertain scenarios. So there are definitely techniques out there and tools that are being developed, and I think very much in the kind of applied science area of the Met Office, there's a massive drive around how do we make this information actually useful and to inform decisions, and working closely with stakeholders to try and understand how that can be done.
Jonathan, do you want to comment?
Sorry, I've lost my thought. The complexity of presenting that probabilistic spread is a big question. Is what we're hopefully leading up to in our problem statement for this workshop at the end of this session. So we already produce a long-term power system analysis looking out to 2050 through the future energy scenarios, and we do that using 4 boxes. So these 4 scenarios that Chris alluded to. I think the important thing is that we're transparent about the source of data that we're using for assessing the climate signal over the top of that, so that we can open that up for other people to carry out similar assessments, and that will help support which decisions need to be taken for investing in the future power system.
Yeah, that sounds good. Chris, did you want to add anything?
Yes, well, so for the last 18 months, I've been working on COVID predictions and talking to governments and the press about that, and that's impressed me very much. The fact that when you make any prediction, you have to say what the level of uncertainty is, but at the same time, just because it has a level of uncertainty doesn't mean it's wrong, and it's often been quite a battle explaining that to decision policymakers or the media. The uncertainty doesn't mean you think it's wrong. And the great thing about modelling, of course, is that you can, to a degree, quantify your level of uncertainty. So I think it's essential that you are honest, but at the same time, say that we are still guided well by the models.
Yeah. I've got another question here. So I thought we'd run out of questions, but we had a last minute flurry. Have you been able to investigate the impact of the effect of combined weather variable hazards? For example, overhead line icing and high winds, because obviously that increases the risk, doesn't it?
I can say that icing and high winds were both included in the model.
That's good, thanks. And somebody's asked about how we're collecting collective response to this, so that it can help other organisations. So I think, Laura, I think you touched on this in terms of some of the data that you're providing to people, but I don't know whether anyone wants to comment on that. How do we share knowledge? Is always a problem, I think. Laura, do you want to say anything?
I think in our experience, we've just tried to kind of get out there and attend as many things and talk to as many people as possible. But I think, yeah, it's always a challenge to reach everyone. Making everything publicly available is really helpful. I guess writing journal articles, and doing kind of, Twitter and LinkedIn, that sort of thing. I think is
well, if you want to publish any of this in our journal, we're actually on that. One of the things with multidisciplinary research is often it lends itself better to programs rather than individual projects and papers. So actually, we're doing quite a few special issues actually. So that I think that's a good way of gathering, because it also draws in people from different disciplines as well, so that they share across that. But does anyone else want to comment on that point? Chris?
Well, I just think communication is essential, and I'd very much like to publish in our journal.
Thank you.
It's one of the one of the components of the MIVOR project, for example, is a network innovation allowance project. So it was funded as part of our regulatory arrangements, and the conclusions of all of those are published on the Smarter Networks portal, which is run by the Electricity Network, or the Energy Networks Association. Yeah. So the MIVOR project is there, and the summary report's available, and we discuss the more detailed if questions come through.
So that very much reaches the sector, presumably, but it's a question of how you reach other sectors is a more tricky one, isn't it? Yeah. No, and I think that's a problem for lots of work. There's so much stuff being published now, particularly around climate change. It's hard to see the wood for the trees sometimes. But I've got one final question, which I think we've probably got time for, which is for this area, what would success at COP26 look like? So I'm hoping that you can come up with something a bit different to what, everybody's been saying the same things, which is good, but who would like to go first? Chris, do you want to go first?
Well, I would say a real commitment to renewables would be fantastic, so that we can plan forward on the assumption that the huge majority of our electricity will be generated by renewables, as is being projected. So let's make sure that happens.
Jonathan?
So I would say a success would be an increased awareness of the potential risk to infrastructure through the climate projections, and making sure that we keep our focus on the continued reliable and secure system operation.
And Laura?
Yeah, I think sort of similar to that. While obviously it's extremely important that we have a really hard push towards renewables, really understanding that, as I said, there's that sweet spot between mitigation and adaptation, and making sure that it's done in a resilient way, that's kind of not going to cause issues with kind of power outages and that kind of thing.
So I'm going to ask Matt now, because I've got a few more questions here. Have we got time to do a few more questions?
We could probably do one or two more. Yeah, maybe.
Okay. Right. Where are we? It says here, the predictions for the uncertainty factor represents a level of confidence, a term we use in finance. So I think that it's that there is a question about terminology. Well, we don't talk about uncertainty, but we talk about levels of confidence, and certainly the climate community has done that. I don't know whether anyone wants to comment on that communication aspect, because I think that's a good point actually. We have to be careful about what words we use, because they're received in a particular way. That uncertainty suggests we don't know, and I think you raised that before. But does anyone want to say anything more about that? I don't know, Chris, Laura, no? Okay.
Well, so in my community, it's always called uncertainty. I'm not sure what that, but does that mean mathematicians are inherently pessimistic people?
Yes, I think so. Laura?
Yeah, similar. It's absolutely a key point. I think level of confidence may also suggest a lack of confidence, as that's also linked to uncertainty. So it's around I think it's a really key challenge, and I think it depends on the sector you're talking to and the people that you're talking to. And I think similar to what Jonathan said, being very transparent about what you mean and how you've come to that word and that statement is really important, rather than just kind of saying it without any explanation.
And then I've got a question for Jonathan here. How might resilience improvement be quantified with respect to growth of embedded battery energy storage?
So it's a component of future energy scenarios, looking at how storage needs to fit into that as part of the resilience mix. So identifying the quantity that's required, how that's supported by interconnection, and how that goes alongside an increasing renewable component. And then the economic assessment of that follows on through our shorter cycle planning processes.
So I think all the questions came in at the last minute, so I'm going to stop there and hand back to Matt, who's going to introduce the challenge session.
Wonderful. Thank you, Vicky, very much. And thank you, panel. Thank you, Chris, Jonathan, Laura, for that fantastic session. And apologies for people who didn't quite manage to get their questions in or answered. There is an opportunity, as Andy mentioned, to put your questions directly to speakers through the CVent platform, which you will have joined through and book one-to-one. So I encourage people to use that session or use that capability to ask any questions you haven't had a chance to, or reflect on later and suddenly come to the realization there was a question that you really needed to answer that wasn't covered. But at this point, I'm going to introduce three challenges that have been posed to us, and then also introduce this idea of these mathematical study groups, which we are using to build on what Vicky was saying, to increase this cross-sector collaboration through these intense research workshops, which we've been running a lot with Chris and others on COVID. But next week, we'll be running something specifically on energy systems and resilience. And these three questions that you'll hear shortly will be the subject of those workshops. So on Monday and Tuesday next week, University of Bath Institute for Mathematical Innovation and KTN will be virtually hosting over, I've written 30, but I think it's just jumped up to about 60 research academics virtually to look at the challenges you're about to hear, analyse relevant data sets for them with the end users and the problem poses, develop and compute models over 2 days, and discuss them, as we won't have time to discuss them today, but discuss them in detail over 2 days, come up with ideas of models that could work, relevant data sets, and pull out some insight. So I'll introduce the three problems in turn. As I said, there's not time for a discussion after each one, because they're 10-minute introduction to the problem. But if you are interested as a researcher, university researcher, do get in contact about joining the session next week. And for anyone else, do get in contact with the presenters on the platform. So with that, I will hand over to Chris Retzler. Now I will share my screen and provide you with remote control, Chris. So if you want to unmute yourself and begin, you should be able to take control of my screen. So Chris is the founder and technical director at Motion Energy, who's going to outline a challenge on wind and wave power complementarity. Chris.
Thank you very much, Matt. So Motion Energy's business is the design and construction of wave energy converters. That is to say, machines which take the mechanical energy embedded in ocean waves and turn it into electricity. The slide has not moved on, Matt.
Chris, I'll move it on for you.
Thank you. Thank you very much. So we completed a prototype this year and deployed it in Orkney at the European Marine Energy Centre. So bottom left there, you'll see a picture of the machine, which is a hinged raft, and its elaborate shape is designed to make it highly efficient at absorbing energy from ocean waves. Top right picture shows you the machine actually deployed at the EMEX site, and you can see it flexing there about the hinge, which is 2/3 down the length of the machine. Waves are coming from the right-hand side. Bottom picture shows you instantaneous power out of the machine with peaks there of 40 kilowatts and averages of 5 to 10 kilowatts. Next slide, please, Matt. Now, we're interested in the integration of wave energy with wind power. And they're rather different beasts. So a wind power is dependent on the irregular nature of wind. It varies in both speed and direction. And wind turbines take out one of these variables, that of direction, by yawing by changing the orientation of the machine with respect to the wind. So they face into the wind, and therefore the amount of power they generate just depends upon the speed of the wind. And the graph shows you how a 1 megawatt to a 10 megawatt machine typically behaves in wind speeds of 0 to 25 meters per second. If you prefer that in knots or miles per hour, just double that figure. So 0 to 50 knots or miles per hour. They have a cut-in speed. And the power builds up gradually into the maximum power in the rate at the rated speed, and then they have a cutout, and that cutout's important as well. So economically, you adapt the rated speed of the wind turbine to the available wind regime, and you adapt the cutout speed to the extrema that occur in that wind regime. So there's no point in over-constructing the machine, making it stronger than it needs to be. That just costs you money. So you make it as strong as it needs to be for the wind climate. Next slide. And here we see a distribution on the left-hand side of actual wind speeds at a northern Scotland site. So you get wind speeds over this 0 to 25 meter per second range. Very little occurrence at the very low wind speeds because the air is pretty well always moving, but it builds to a maximum occurrence at around about 8 meters per second. On the right-hand side, you'll see the resultant wind turbine output. So here what we've done is to multiply the turbine transfer characteristics, turbine power curve by the wind speed occurrence, and we get this modified distribution on the right-hand side that has less power in the lower wind speeds on the left-hand side of that graph. And at the top end, at 25 meters per second, where the cutout applies, there's 0 power out. Next slide, please. It's a rather different case for wave power. So wave power depends both on the height and the period of the waves. Ocean waves are irregular because they're driven by the wind. The action of the wind on the ocean surface is creating the waves. But it's not just speed that matters here, it's the height of the waves and the period. They do have directional spread and, around a main wave direction, but that again is taken out in the same way as it was for the wind turbines, because the wave energy converter can yaw to face the principal wave direction. So the features of this graph on the left-hand side are that the power output from the machine is shown in color, and the lighter the color, the more yellow the color, the greater the power. So it's high in high waves and in waves of round about 4 to 5 seconds period. In very high waves, we reach a limiting power, but it stays at that limited. There's no cutout. That's a feature of the motion wave energy converter. Next slide. So here we take the sea state occurrence, which again is a two-dimensional graphic, two-dimensional diagram. And we can see that although sea states can arise over a very broad range of conditions, they tend to be concentrated. And they, for the wave site that the prototype is in, which is a small scale sea, it tends to be focused around about 5.5 second period and round about 1.5 meters HS. Now, when we do the same as we did for wind turbines, we multiply by the transfer characteristic, the power matrix of the machine, we get a narrowing of that area because of the resonance of the machine. So it tends to be contracted a little bit along the period axis, but it's extended along the height axis. So I want to say as well something about scaling here. We're proposing to have co-located wind energy and wave energy. That is to say, we would hope to install wave energy machines where wind farms are. The wave energy resource is that of the North Atlantic. For the UK, it's for the North Atlantic. The North Atlantic is one of the most net energetic climates, wave climates in the world, with about 75 kilowatts available per meter of coastline. So for the 1,000-kilometer coastline of the British Isles, we have about 75 gigawatts of raw mechanical energy incoming. So that translates with machines that are reasonably efficient into a very large amount of contribution to energy consumption for the British Isles, the UK and Ireland. So how do we adapt to this? Well, the machine which you saw in the first slide is a 10 kilowatt machine, and its length was 20 meters. Its resonance was 4 to 5 second period. In order to adapt to the North Atlantic, where the waves have typical periods of 8 to 10 seconds, we would need to quadruple the length of the machine while keeping its proportions the same. That would move its resonance up to 8 to 10 seconds. It would have a dramatic effect on the increase in power. The power would increase by a factor of 100, and we'd move from a 10 kilowatt machine to a 1 megawatt machine. Wind turbines at the moment are in the range of 10 megawatts for offshore wind. But there's a lot of space between turbines. So we could easily fit 10 1 megawatt machines between in the spaces between these 10 megawatt wind turbines. So we can make a very significant addition to a wind farm with these interstitial wave power units. Next slide, please. What's more, not only can we add power, we can add power which is uncorrelated with the wind. So if you look at the top plot there, we have a mean wind speed record for the Atlantic-facing site of the European Marine Energy Centre. So this site is at Billia-Crewe, and it has direct aspect to the North Atlantic. The wind speed, as you can see, are highly variable, but the associated HS, the associated waves, which are incoming on that bit of coastline at Billia-Crewe, are more steady. And this is because the ocean acts as an integrator of wind energy. The Atlantic Ocean, of course, is huge. It's 4,000 or 5,000 kilometers across and 10 to 20 million square kilometers. And wind energy is being integrated over that entire area and turned into wave energy. And that's why the output is smoother. So the motion wave energy converter benefits from this smooth energy supply. And the motion wave energy converter also continues to generate high power and extreme waves. It doesn't cut out. So in both these ways, it's complementary to the electricity that would be generated by a wind farm in an offshore site of Scotland. So the challenges to the space and geospatial teams will be, can wind and wave power complement each other? I think it's pretty clear that they can, but the extent needs to be determined. And how can geospatial monitoring and modeling contribute? Because these will be very valuable tools for projecting and instantaneously determining the output from wind and wave combined as an input to the national grid. Thank you.
Thank you very much, Chris. That was fascinating. For me, a great introduction to wave energy there. So thank you for doing that in such a short space of time, and lots for our researchers next week to get their teeth into. So our next challenge that's going to be looked at next week is from KrakenFlex. We have Dr. Nick Good, who's senior data scientist there, who's not able to join us today, but has pre-recorded a 10-minute video. So let me share my screen with sound, and you'll hear the challenge of flexibility for future electric heating.
Hello, I'm Dr. Nicholas Good from Kraken Flex, Senior Data Scientist at Kraken Flex, and I am giving you a presentation on the flexibility of future electric heating. And we'll be finishing the presentation with some questions that you might find interesting around this topic. So, right, contents. I'll give you an introduction to Kraken Flex, and I'll talk about the UK's heat pump ambitions, and then a bit about the challenges of heat pump integration. So the problems we're going to be faced as we try and implement all of these heat pumps. And then I'll pose some questions that you might find interesting to answer, geospatial related questions. So what does Kraken Flex do? We're a software as a service company, so we provide software to other companies, and it's basically providing tools to balance generation and demand, keep the grid balanced at all times, so balancing supply and demand. We're enabling flexibility, because without flexibility in the grid, you're going to have problems. Another way of looking at it is we bridge the gap between assets, so flexible assets such as you see there on the left, batteries, heat pumps are one, but even wind turbines and solar PV can be flexible, because you can turn them down. So many different types of assets, and we've integrated with many different types already. And then on the other side, we have the market. So trading, wholesale, within day ahead, balancing mechanism, different ancillary services, any way you can make money from changing when you're consuming or generating energy. And we're asset agnostic, we're market agnostic, so we can play with all of those assets in all of those markets. And our offering can be broken down into 4 groups, really. Control and dispatch, so being able to control the assets, get them to do what you want them to do. That's might sound quite simple, but actually it's very tricky, particularly to the level of confidence that some of these markets need. Providing events and notifications, so you know when something's going wrong with your asset, or when some other interesting thing has happened, instant notifications. Post hoc reporting and analytics, including settlements, so you can prove that you did what you said you were going to do in different markets. And then optimization and modeling, so this is ahead of time, modeling a case to look at the value of that case, and then in real time optimizing against real price signals, so you can go and trade in different markets. So heat pump ambitions. Well, you might have seen this from a few months ago, the 10-point plan, where there was a very widely circulated aim to be installing 600,000 heat pumps per year by 2028. And you know, it's not just the government touting this, the national grid scenarios, even their most conservative scenarios are seeing a large increase in electricity demand for heating homes, which most of which will be heat pumps. And in some scenarios, it's quite a large increase. And it's not just the UK. The share of households purchasing heat pumps for heating hot water in selected regions. So that's mostly sort of developed countries. And yeah, we're seeing a lot more. The dark blue at the top is heat pumps. So you're seeing that increase a fair bit in collection of other geographies. But as I said, it's not simple to increase this number of heat pumps easily. First of all, this is a plot of the winter and average winter and max day electricity demand for 2019 pre-pandemic, and you see there's already some large increase during the day and some peak, particularly in the evening. And this large penetration of heat pumps is going to increase peak electricity demand, so it's going to build on top of this quite substantially, and just gives a bit of an indication of how much it might increase. So it's very hard to get heat demand data. So this is a survey of 19 sites from an academic paper, and you're seeing serious morning and afternoon peaks, and a large peak coincidence factor of 41%. So they're all likely to be peaking at the same time. And if you consider that there's 23 million houses just in England, plus also Scotland and Wales and the GB electricity system, there's going to be a big increase in peak demand due to adoption of electric heating. It won't be quite like this, because heat pumps they operate better if you operate them consistently. So you might see a flatter load shape, but it's definitely going to be an increase, especially in peak demand. So that's your generation capacity concerns. So having enough, being able to supply the electricity that the whole grid needs. But there's also more local issues. because large penetration of heat pumps can cause network problems. So these are graphs from two graphs from a paper which conducted a probabilistic impact assessment on 3 real UK low voltage feeders in the northwest of England. So on the left there, you see that on these feeder 1 and 4, as soon as you're getting above 30% penetration of heat pumps, you're getting voltage problems on those feeders. And then on the right, you can see that some at quite low penetrations, but most, once you're getting up to sort of above 60, 50, well, 50 actually, 5 of the 7 feeders there are experiencing capacity problems at the head of the feeder. So basically, these networks are really going to struggle to accommodate 100% transition to electric heat pumps without mitigation, that is. And also it's worth saying that this is for a cold day. These are for a cold day. These aren't the coldest day, so it could be worse for the coldest day. Yeah, but we should also remember that heat pumps are also a solution because they can be operated flexibly. So you can utilize building thermal inertia. So especially UK buildings, typically made of brick. They have cavity wall insulation. So you can effectively store heat in the fabric of the building, and this could allow you in a well-insulated building to maybe switch your heat pump off for 1, 2, 3 hours with little effect on thermal comfort. So you've got flexibility from that. You can also have flexibility enabled by thermal energy storage. So you pair your heat pump thermal energy store, generate heat perhaps at off-peak times, and then turn the heat pump off and drain down that hot water store to coast you through peak times. That's one way you could a heat pump can enable flexibility. And both of these can be helped with the adoption of thermal phase change material, however. So storing heat by changing the phase of some material, typically turning a solid to a liquid, and taking advantage of the latent energy. And then there's also substitution. So although one of the reasons for adopting heat pumps is to move away from gas boilers, there may be a case for pairing a heat pump with small gas boiler that can be used at the very peak times. So when everybody on your street is turning on the heat pumps, it's a super cold day, you actually might want to operate that gas boiler. You're going to be releasing emissions, of course, but if you pair this with direct air capture of emissions, or even point air capture, I can't imagine that would be cost efficient. Then that might be a useful source of flexibility. And a recent study by Imperial College London suggested that if direct air capture was to reduce sufficiently in price, this would be the first place that you would use the license. This is where you would emit the carbon that you wanted to remove. Basically, this is where you would use that budget of carbon, because the upgrade of networks, especially, is so expensive. And also, of course, this could be a hydrogen boiler. That's a different topic there. So that's given you some context to the challenge and the flexibility of heat pumps. But what are the specific questions that I think might be interesting? Well, I've got 2 here. One is, given the maximum electricity import limit, how much thermal storage of those different types, or you might want to focus on one, perhaps thermal energy storage, how much would you need to maintain thermal comfort in different locations? Because obviously cities, countries, north, south, peak or lowest temperatures will vary a lot. How much would you need to get through 1 in 5, 10, 20, 100-year temperature lows? And then the second one, if the flexibility is provided by backup gas boiler, how much CO2 would be emitted in those different scenarios? And you might need to look at multiple scenarios of max allowable electricity demand. So, if your peak electricity import for your house is 3 kilowatts, 6 kilowatts, 9 kilowatts, that's going to affect how much you need to use the heat pump versus the gas boiler. And you might, you might have a limit to, because your feeder has a physical limit. So that might be a salient constraint. So this is a couple of ideas. I hope you find the concepts, the area interesting, find the questions interesting. Down my contact details, but I think there's also going to be a session in which you can ask me questions. So thank you.
So thank you very much, Nick. Again, the session he refers to is this research session with Bath University next Monday and Tuesday, and I can see some questions are coming through. Again, we don't have time to answer them in this session, but please do get in contact with the speakers, any of our speakers, through the portal, this event platform, which has brought you here today, and hopefully you can connect with the speakers then. So finally, I'm going to pass back over to Jonathan Barcroft from National Grid ESO. And I think for this particular challenge, Jonathan, we're coming back to the topic of representing uncertainty. So Jonathan, if I can pass over to you.
Hello, thank you. So at National Grid ESO, understanding the hazards of extreme weather and changing normal weather to the power system over the next 30 years forms part of our long-term system planning. The MIVOR project has given us a better opportunity to understand how the risks to the system are changing under a changing climate. The power system in Great Britain takes electricity from where it's generated to where it's needed, and it spans the length and breadth of the country, and is such as sensitive to weather conditions. Our generation mix is increasingly weather dependent, and all technologies, including thermal, have sensitivities to weather-related hazards. The largest factors in determining the demand on the system are the calendar and the weather, and a change of 1 degree Celsius in cold conditions could drive a 500 megawatt increase in demand nationally. With the electrification of heat and cooling, this is likely to increase. Our role is to balance that system second by second so that supply and demand are always in step. The geographical spread of generation and demand also means that the network needs to be capable of transporting it from where it's generated to where it's needed. Historically, this has always travelled from north to south, from large thermal power stations in the north, down to the demand in the major cities in the south of England. Now the flow of power on the system depends on the weather. Large quantities of weather-dependent generation, like wind and solar, are spread across the system and can mean that the flows vary significantly throughout the day. Our future energy scenarios suggest that there could be between 31 gigawatts and 47 gigawatts of offshore wind connected to the system by 2030. Looking across our future energy scenarios, the network options assessment process has identified a potential of 17 to 28 gigawatts of interconnection capacity between GB and the European markets. For reference, we currently only have 6 gigawatts of interconnection. So that's a 3 times increase. This increases the relationship between energy and GB and the weather conditions across Europe. We maintain a continual cycle of review of the power system to make sure that it remains secure, sustainable and affordable. This cycle starts by understanding the range of scenarios that deliver a net zero power system by 2050. We publish these in the future energy scenarios. We use those 4 scenarios of expected generation and demand requirements to evaluate what changes are needed to the transmission networks. And these form the electricity 10-year statement. From the electricity 10-year statement, we undertake economic assessments of the proposed network solutions to identify the most cost-effective ways of achieving the network requirements. This results in investment recommendations for the priority of each network reinforcement over the next 10 years. Now, alongside these network-based options, we assess market-based services or other innovative methods for resolving constraints, and these are published in our Pathfinder projects, System Operability Framework, and our markets roadmaps. In our long-term planning, we currently use historic data and historic relationships to make projections into the future. We then apply estimations of the changes to be expected from emerging technologies and changing patterns of use, such as the heat pumps referred to earlier. This provides information on what has happened, but is slim on what could happen. For example, the cold weather event that occurred in Texas in February 2021 was outside the range of historical weather data. Our work for modelling climate change is primarily focused on the impacts of extreme weather events through projects like MIVOR and through our TCFD components of our annual report. This forms a component of our modelling. However, we're also aware of the potential changes to conditions during normal operation, during the new normal weather conditions. So the meteorological community has developed climate models to simulate a range of scenarios. These are determined by different greenhouse gas emission pathways. MIVOR shows that this data could be harnessed in the analysis that we carry out at National Grid ESO and can be used by other industry parties. However, it's not simple as collecting that data and running it through our processes. It's important to engage with external experts and to ensure that we're using the best data set for our applications. We hope to achieve a consistent approach for considering climate change throughout our modelling. So this leads on to some of the questions that we have. We need to consider which representation concentration pathways could represent the possible range of changes of future climate, and how these should be selected or combined to define system requirements, and how that can be represented through our existing analysis to give confidence on expected solutions. We also are aware that changes to the system take time to implement. Therefore, it's critical that we use the right data to drive cost-effective solutions. Our future energy scenarios and the associated planning cycle are already a complex analysis of the energy system. These span 4 different scenarios for achieving net zero and look 30 years into the future. We need to present a range of scenarios on the system due to both climate and other inputs, and make sure that's as succinctly as possible. Our approach should be developed in a way such that our long-term assessments are aligned. By developing best practice, we can ensure that our analysis remains comparable while using transparent data sources. We're looking for recommendations on how we can select and combine different climate projections to produce a robust analysis of future system requirements, and how that can be presented in a format similar to the future energy scenarios, the network options assessments, and our markets roadmaps. And we're also interested to understand how we can model the changing climate across Europe and its interaction with those interconnector flows as we move from the 6 to 7 gigawatts that we have connected now, and we move into the 17 gigawatt world, where we're connected to power systems in Norway, for example, recently come online, or onto mainland continental Europe. So these are the topics that we're hoping to cover in the 2-day workshop next week, to understand how we can transparently represent these inputs into our model, and an understanding of those confidence intervals of where these variables are going to sit.
Thank you very much, Jonathan. Some nice, easy questions posed there. No, very hard ones that I'm glad we have a multidisciplinary group of modelers, climate scientists, statisticians joining us next week to look at all 3 of those problems. So thank you very much, Nick, Jonathan and Chris. And with that, I will pass back to Professor Pope to close us out, give us a few closing comments. But from our side, thank you very much for everybody for taking part and for joining. And over to you, Vicky.
Thanks, Matt. So, I mean, I think Jonathan presented some very clear challenges that are going to address next week, which I think will make for a very interesting session. So I hope that that goes well and you're able to address some of those. Some of the things that struck me was that there are big, in terms of the biggest challenges, I think there's obviously the challenge of understanding the demand for electricity, and that's and human factors involved in that. I think the changes in the supply network and the dependence of that network on the weather, and how that might, the changes in the climate change might influence that. Building a resilient infrastructure with the kind of new technologies that are coming in for that. I just wanted to comment on, I think a lot of your planning is in the next 30 years, but actually the biggest changes, of course, will come in the next, the following 50 years, and whether you also need to look at that infrastructure on that timescale. I don't know, maybe it doesn't have that lifetime, but some things may well do, and whether you need to look at, and that's where you'll see much bigger changes, which could change the way that you operate many of these things completely. And the other thing I was going to raise was about extremes, and there's quite a lot of work being done. So the very high resolution models that Laura talked about, where you've got 2 kilometer resolution, that's a way of looking at extremes, and whether the kind of, by comparing that with the historical data, it might be that you bring out a different relationship between extreme events and the mean events, and actually that there are some kind of really unexpected things that might happen. And the other thing that people have used, what the seasonal forecast models to create basically thousands of years worth of data, rather than just going back 100 years to look at extreme events. And using those models, you can actually identify events that have never actually happened but are statistically possible. They're very low probability but very high impact events, and that kind of analysis could be useful and might be something to consider in your workshop either next week or in future ones. So the other thing that struck me was about the challenge talks, which I thought were really interesting. The way that we use new energy sources and how we might combine those energy sources to generate electricity, and many of those again are weather dependent, and how you can get information about that. There's always the difficulty with losing historical information to characterize a site, for example. If you've only got a few years of data, that may not characterize for very long periods. There are very long timescale natural variability, quite apart from the climate change, that can affect wave energy, for example, on decade timescales. That some of the weather models again can give you a handle on some of that perhaps just observational data on its own can't do that. So that might be something to consider as well. And the integrating assets, I think, kind of brings a lot of this together. So I was interested in the role of heat pumps because we fitted a heat pump in our house about a year ago, and there's certainly a huge amount of interest in it. Lots of people have asked about it, and I wonder whether that could accelerate faster than we think in terms of people installing them, and that obviously will present some challenges to the network. So I think this, it's been a really interesting session. I hope that the people watching have enjoyed it, and that maybe some people will watch it afterwards as well. And I think there's some very important questions that you're going to be addressing in the workshops next week. So with that, I will close the session unless there's anything more that Matt wants to say.
No, I think that's a fine summary. Thank you, Vicky.
Thanks, everyone.